My name is Yong. I'm from the Data Storage Institute in Singapore. Today, I'm very happy to have this opportunity to present you our work. So the paper title is NVTree, Reducing Consistency Cost for NVM-based Single-Level Systems. So here's a quick overview. The major advantage of the next generation of NVM, such as STT-RAM, RAM, is that it has DRAM-like performance and persistency as well. So this gives NVM the opportunity to replace both DRAM and the disk. As data is stored persistently in NVM through memory bus, data consistency becomes an issue. So we found providing data consistency for data structures like B+Tree or its variants in non-volatile memory is very expensive. So this is mainly because ordering memory writes introduces a very big overhead for in-memory data processing. So moreover, to guarantee the atomicity of writes, logs may be needed because CPU can only support atomic writes within a limited size. Last but not least, we reviewed that the most of the ordered writes in tree structure are spent on sorting entries inside the tree nodes. So based on these findings, we propose NVTree. NVTree is a B+Tree variant which provides data consistency without logs, and it is cache optimized. The main idea is to decouple leaf nodes and internal nodes. For leaf nodes that store the real data, ordered writes are enforced to provide the data consistency. And we further reduce the amount of cacheline flushes to make the ordered writes by adopting unsorted keys with append-only scheme. So for internal nodes, we found it is reconstructible, so no consistency is enforced. And performance-wise, we organize them in a cache-optimized layout to keep the keys sorted to facilitate the search. Our experiment results show that NVTree can reduce CPU cacheline flush by 82 to 96% compared to the competitors under insertion workloads, and then can be 12 times faster than existing approaches under write-intensive workloads. We also built a KV store prototype called NVStore, which can be up to 4.8 times faster than Redis under YCSB workloads. So let's first look into the details of our motivation. The next generation of non-volatile memory provides DRAM-like performance and disk-like persistency at the same time. So this gives NVM the opportunity to replace both DRAM and disk to build a single-level system. So this is a traditional computer architecture. Imagine we replace the disk with a disk and the DRAM with NVM in the traditional computer architecture. And then we connect the NVM to the system through the memory bus in the same way as DRAM, like this. Then we will be able to get a system with only one level. So the data which requires to be saved persistently are stored in NVM, while the rest can use the DRAM for data processing. In the traditional design, as data is stored persistently on disk, so the persistency boundary resides on the I/O bus. However, in a single-level system, the persistency boundary moves from the I/O bus to the memory bus. As a result, the in-memory data consistency is required. So ordered writes are fundamental for keeping data consistency in a pointer-based data structure, such as trees, where pointers must be written, where data must be written before the pointer points to it being written, or in a logging approach where logs must be written before updating the data in place. So, however, ordering memory writes is not as easy as those to disk because CPU are designed for volatile DRAM. So memory writes may not be in the same order as programmed. So due to the CPU reordering and CPU cache. So to enforce the order of memory writes, we need to use mFence and seal-flush instructions. So mFence issues a memory barrier which guarantees the memory operation after the barrier cannot proceed until those before the barrier complete. But it does not guarantee the order of write back to the memory from CPU cache. So on the other hand, cacheline flush, the CO flush instruction, can explicitly invalidate the corresponding dirty CPU cachelines so that they can be flushed to NVM by CPU, which makes the memory write persistent eventually. For example, if you want to make sure the write 1 finishes before write 2, we can issue the writes and the combination of M-fence and CO flush in such a way. However, ordering memory writes using M-fence and CO flush is quite expensive. As an illustration, we implemented a standard B+Tree and its consistent version using logging. We also implement a well-known tree structure for NVM called CDDS-tree and its volatile version. For both trees, their consistent version is much slower than their volatile version, 16 times slower for B+Tree and 20 times slower for CDDS-tree. Why? So we measure the CPU's L3 cache misses for all the trees and find out the reason. So the performance degradation is due to the amplification of CPU cacheline invalidation when using cacheline flush instruction. So to optimize this, we further investigate the amount of cacheline flush for different purposes. We found that more than 90% of the cacheline flush is spent on sorting entries in leaf nodes. Imagine inserting an entry in a leaf node because both trees keep entries sorted in their leaf nodes. So all the entries after the insertion position have to be shifted to the right. So to keep the data consistency, such shift needs to be handled carefully. So for log-based trees, like the B+Tree, log must be written before shifting. For CDDS tree, M-fence and CO flush must be executed after shifting each entry. Both produce large amount of cacheline flush. So to address these issues, we design a new tree structure called the NVTree to efficiently provide data consistency. So here's an example of NVTree. To reduce the amount of data that needs to be needs ordered memory writes, we first decouple tree nodes to critical data as the leaf nodes, and the reconstructible data, the internal nodes, or here. So leaf nodes are stored in a single linked list and can also be accessed by the parent of leaf nodes, the PON, through these links, like just like B+Tree. Then ordered writes are only enforced for updates in leaf nodes. For internal nodes, both because they are always reconstructible from leaf nodes, so ordered writes are not enforced. In leaf nodes, entries are encapsulated, and more importantly, they are unsorted and always appended into a leaf node, so that the cacheline flushes can be significantly reduced. On the other hand, internal nodes are stored in a cache-optimized format, so they are stored in a consecutive memory space. They are cacheline aligned, and they are located without pointers and highly concurrent. So let's first look into the details of the internal node design. All the internal nodes are stored in a continuous memory space, and each of them is aligned to CPU cacheline. So as long as we have the node ID, its memory address can be calculated using the memory address of node 0 and the size of each internal node. Therefore, no pointers are needed to locate the internal nodes, including the parent of leaf nodes, because they can always be located through offset. But PONs have to store leaf node pointers to locate them as they are dynamically allocated. At the same time, no consistency is required because internal nodes are reconstructible. So here's an example of locating the next internal node during the tree traverse. If an internal node in a tree have m children, then the memory address of the case child of the node can be calculated using this equation. So let's move on to the leaf node design. Each leaf node is dynamically allocated as needed, and they are aligned to the cacheline size. The persistent data, for example, in our case, the key value pairs, are encapsulated in a data structure called leaf node elements. To reduce the consistency cost, leaf node elements in each leaf node are unsorted and appended only. So the penalty of CO flush for entry shifting shown earlier is eliminated. To search in a leaf node, we identify the boundary of the search according to the n-elements field here before scan for the target. So to keep the data consistency in this case, we must guarantee there is no partial modification. So this can be achieved by 2 steps in order. Step 1, we append the leaf node elements of the new data, followed by mFence and CO flush combination. Step 2, we atomically increase the n-element field by 1, followed by mFence and CO flush combination also. So since the size of an element is only 8 bytes, modern CPUs such as Intel's can support the atomic writes in such granularity. So those 2 steps can guarantee any undergoing or unfinished modification due to system failure is not visible to others as long as we use the n-elements field as the search boundary. So on the other hand, given the append-only scheme of writes and the search boundary idea, then we are able to do log-free reads naturally. So all the tree write operations such as insertion, deletion, and update are transformed into appending leaf node elements. So for example, we have leaf nodes with two leaf node elements representing 2 entries, 6A and 8C. The first step for insertion in a new entry, 7B, the leaf node element with a plus flag is appended. For delete the entry 6A, the leaf node element with a minus flag is appended. So for updating AC to 8Y, 2 elements with a minus flag and a plus flag are appended. So after that, mFence and CO flush are issued to guarantee the modification reaches NVM. So the space occupied by deleted entry here will be reclaimed during split. So the second step is to atomically update the n-elements field in the leaf node. So before atomically update operation finishes, all the appended leaf node elements are not visible because n-elements is used to identify the search boundary. So finally, mFence and CO flush are also issued to guarantee the n-elements field is written in NVM. So as the amount of data updated during the split usually exceeds the size limit of the atomic write supported by CPU. So to avoid the inconsistency such as invalid pointers or data loss, we can either use the traditional logging approach like the B+Tree or frequent mFence and CO flush like in CDDS tree. But these approaches are both expensive as shown earlier. So in contrast, our NVTree avoids partial split by manipulating the data visibility and utilizing the small atomic write. So in NVTree, all data modified by unfinished split is invisible upon system failure, only becomes visible after a 8-byte atomic write. So here's an example. Suppose we have a full leaf node here needs to be split. We first create 2 new leaf nodes, copy the valid leaf node elements, and link them properly. At this point, the new leaf nodes are only visible to the split process itself. Then we insert a separate key to the parent and link them properly. So far, the new leaf nodes are still invisible to the entire leaf node list. So because the entire leaf node list is actually the critical data, so the critical data is still intact at this stage. So finally, we update the sibling pointer in the left leaf node with an 8-byte atomic write. So to finish the split and make the split result visible to the others. So due to the existence of those leaf node elements with minus flags, a full leaf node may not have much valid leaf node elements, so the expensive split may be avoided. So comparing to a traditional tree, NVTree has some additional operations like replace and merge to optimize the space utilization. So based on the minimum fill factor, one of the 3 operations may be executed. So you can refer to our paper for more details about these 3 operations. So a special operation in NVTree I want to mention is rebuilding. So as the position of all internal nodes and PONs are fixed upon creation, they are not allowed to split. So if the one PON is full, there is no space left to accommodate incoming separate keys from leaf node split. So to overcome this issue, we introduce a new operation called rebuilding in NVTree. For example, if the PON is full like this with 5 keys and 5 leaf node pointers, all the internal nodes will be rebuilt. All the internal nodes will be rebuilt to make more room in PONs. So you can see now every PON have 4 empty slots for new incoming separate keys from leaf nodes. And you can see now in the internal nodes we have 5 keys. As internal nodes do not have any pointers, it leaves it 5 more empty space. So during normal execution, we can use the key and the leaf node pointers in PONs for rebuilding, like moving the keys to internal node and using the pointers for the new PONs. So this procedure we call it rebuild from PON. However, if the data in the PON is not available, such as after system failure, we can scan all the leaf nodes to rebuild the internal nodes. So we call it a rebuild from leaf node. So rebuild from leaf node is more time consuming than rebuild from PON due to the leaf node scan. But overall, as I will show in the experiment result later, the overhead of rebuilding is neglectable. So while with the help of NVM, the recovery procedure can be quite efficient. So if it was a normal shutdown and the NVM has enough space to hold all the internal nodes, we can write them to NVM before shutdown. So therefore, the recovery can be as easy as one memory read to retrieve the root of the tree. So we also call it instant recovery. However, if we find the previous shutdown is a system failure, we know the internal node information is not available. So we just simply perform a rebuild from leaf node to reconstruct all the internal nodes. So we can do this because leaf nodes are always consistent, and the head address of the leaf node list is always kept at a fixed position in NVM, so we can always retrieve them after reboot. So let's quickly go through the experiment setup and the results. So we use an NVDIMM server from Viking to build a real platform. NVDIMM is essentially the combination of DRAM and flash memory equipped with a battery and the DDR3 interface. So upon system failure, such as power failure, NVDIMM can back up all the data from its DRAM to the flash memory using battery power. And during system reboot, NVDIMM restores the data in its DRAM from flash memory. This procedure is transparent to the users. So during normal execution, NVDIMM behaves exactly the same as DRAM. So we first compare the insertion performance of these 3 trees, the log-based consistent B+Tree and CDDS tree and our NVTree. So for 1 million insertion, NVTree is 8 times faster than B+Tree and 12 times faster than CDDS tree. Such performance improvement is achieved by reducing the CPU cache line flush. For large data sets such as 10 million and 100 million insertion, NVTree always outperforms the competitors. And for the throughput of those trees operation, NVTree's performance is not always the best. So for updates with different node sizes, NVTree is up to 5 times faster than B+Tree and 8 times faster than CDDS tree. For deletion with different node sizes, NVTree is always better than B+Tree, but not as good as CDDS tree with small node size. However, it shows comparable performance to CDDS-tree with larger nodes. Finally, thanks to the cache-optimized design of internal nodes, the write-optimized NVTree still shows comparable search performance to both competitors. So we also evaluate NVTree under mixed workloads. We compare NVTree with already 1 million entries. Then we execute 1 million operations of insertion search combination on that tree. From write-intensive workloads to read-intensive workloads, NVTree always outperforms competitors. So we further investigate the performance improvement of NVTree by looking to the CPU cache efficiency using Intel tool, the vTune amplifier. We first measure the number of loads from 1 million insertion. Thanks to the cacheline optimizations formats, NVTree reduces up to 90% of the number of loads compared to B+Tree and then 92% to CDDS-tree. We then measure the number of L3 cache misses for the same 1 million insertion and observes 83% reduction compared to B+Tree and 90% compared to CDDS-tree. Such result proves the high CPU efficiency of NVTree. We also quantify the overhead of rebuilding by measuring the rebuild time for different insertion workloads. The result shows that the rebuilding time only occupies 0.01% to 2.77% of the total execution time, which is totally acceptable. So on the other hand, the rebuild from PON strategy can be 22% to 47% faster than the rebuild from leaf node strategy. So in the end-to-end performance comparison, we compare our NV store to both volatile and consistent version of Redis. So under status updates YCSB workloads with 5% insertion, NVTree can be up to 3.2 times faster. Under session store YCSB workloads with 50-50 rewrite ratio, our NVTree can be up to 4.8 times faster. Most importantly, NVStore is much more scalable, as you can see from the figure. So due to the time limitation, please refer to our paper for the additional materials such as NVTree, performance simulation on different types of NVM, or how future hardware support affects NVTree. So that's the end of the presentation, and I'm happy to answer your questions. Thank you.
Hi, Michael Condit, NetApp. You, as I understand it, you only make sure that you atomically flush this one value, the list of the number of elements, all the way to RAM. What about the user data itself? How do you ensure that on a power failure that no user data is lost?
So because user data is actually stored in leaf nodes, right? So these leaf nodes will be first write to the NVM, and then using mFence and seal flush, make sure they reach NVM. Then we update the unelements field and do the same thing to the unelements, make sure they reach the NVM after the data is updated.
Thanks, that wasn't clear. So you're using CL flush on the user data, not just the number of elements?
Yes.
Okay, thank you.
Thank you.
John Groves from Micron. I like this paper. This is good stuff. So I'm puzzled by one thing, though. The implication is that the CL flush causes a cache miss on anything that it's been issued on recently. And is that just a limitation of CL flush? Or is that because threads on other CPUs are fenced out of that section of the cache?
So actually, Intel already announced some instructions called the write back instruction. Okay. So it makes sure you can flush the CPU cache line, but without invalidate it. However, so our technology not only optimize for those invalidation, we also optimize for the amount of data for flush. Like we always append only a single leaf node element at the end of each leaf node. That makes us just only need to flush those data enough, right? So if the instruction is actually implemented and we can use it, we can also benefit from that because the invalidation is removed. Okay, thank you.
Time for one quick question, one last quick question. You said that your reads are never blocked on writes.
Yes.
So what do the reads do when you're rebuilding all of your interior nodes?
So for rebuilding, because all the rebuilding need to visit the leaf nodes, right? But if you have enough space in the memory, for example, the DRAM, we can do the rebuilding and with reads at the same time, because we can keep the previous version of all the internal nodes at one portion of the memory and use another portion for rebuilding. So at this time, reads can go through the old version of internal nodes and get their data. However, at the same time, we can do the rebuilding by visiting the leaf nodes at the same time.
And then you swap everything over instantly.
Excuse me?
And then you swap the reads over to the new structure when they're ready, when it's ready?
Yes. When the rebuilding process finished, it will notify the scheduler and will know we will shift to a new root of the tree. Then the incoming reads will go to the new tree for search.
Okay, thank you.
Thank you.
Thank you.
Thank you.